In this lesson, we're going to go over how to find the volumes of solids using perpendicular cross-sections. So just kind of a warning for you guys in the beginning, this is kind of a lot of things you need to visualize or at least understand what it's supposed to look like. I am not the greatest artist. I am putting that forward, so just bear with me on this. So before we do anything with volume, we want to make sure that we can recall the area of different geometric shapes. So for a square, if you have a base of b, your area is going to be base squared. For a semicircle that has a base of b, our area is going to be pi over 8 b squared, and here's the reasoning for it, because we have half pi r squared, your radius would be half of b. For a rectangle, our area is base times height. For an isosceles right triangle, since the base and the height are going to be equal, area is just going to be half base squared. And for an equilateral triangle, our area is going to be root 3 over 4 b squared. And the reasoning for that is that I broke this equilateral triangle up into a 30, 60, 90 triangle and wrote down the sides and then figured out the area from there. So let's find the volume of this cylinder below. So here we have a basic geometric shape of a cylinder. We know that the volume for a cylinder is pi r squared h. We can see here that the radius is 3 and that the height is 4. So if we plug this in and we solve, we get that the volume is equal to 36 pi. And because it's in inches, this will be inches cubed. So when we have a nice geometric shape, we know formulas for volume that we can just plug in and we can solve. But what happens when these shapes are not actual shapes that we know? So can we find volume using integration? The answer is yes. So you can find the volume by slicing. So if we look at this cylinder that we have here, each slice, these red little discs, and again, sorry for my drawing, these red little discs, these are little slices, and the slices have a face of a circle and a width of dy or dx. So the width can change depending on whatever it's going to be. So we call that dy or dx. So each slice will have a volume of the area of the face of the shape times dy or dx, which is going to be the width. The volume is going to be the summation of all of the volumes of the discs or the slices that are inside. So you can think of this as like the candy, the Lifesavers. This could be like a Lifesavers packet. Okay, so you have a cylinder, and then inside the Lifesavers packet, you have all the little Lifesaver candies. And if you take the volume of one of the candies and add up however many candies are inside, you should end up with the overall volume of the little tube. So same kind of idea here. We're taking the volume of one little slice, and then we're adding all of those volumes together. So I'm drawing the same exact picture. I'll go back really fast to this one. So it's the same cylinder with a radius of 3 and a height of 4, but now I'm drawing it kind of laying on its side. So it's the same idea. Here's the height of 4, here's the radius of 3. But now when I draw it this way, I'm making these little cuts and these slices. So I can see here that I have the little disc, which is my slice. It has a circle as a face, and then I have the delta x, which is just my dx, that's my width. And notice here, each slice is a circle and has an area of pi r squared and a width of dx. So let's write this as an integral. So the volume is going to be the integral from a to b, this is just kind of generically speaking, of the area of the shape, which we'll call a of x, times the width, which would be d of x in this case. So let's plug in what we know. So the volume is equal to the integral from where to where. So since we're doing this in terms of dx, we're dealing with the x's. So the x's are going from 0 to 4. So from 0 to 4. And the area, because each of these is a circle, we know that the area of a circle is pi r squared. So we're going to have pi times the radius, which is 3 squared, times the width, which is dx. So I'm just going to simplify this a little bit and say the integral from 0 to 4 of 9 pi dx. So if I take the antiderivative of 9 pi, that's going to give me 9 pi x. And now I'm evaluating it from 0 to 4. So if I plug in 4, this is going to give me 36 pi, minus I plug in 0, so minus 0. So again, I end up with 36 pi inches cubed. So it's the same exact volume that I got from doing the volume the traditional way, but in this case, I use integrals and got the same result. So what happens when they're not normal shapes like a cylinder or something that we know? Okay, so there's two different types of cross sections that you're going to see. Cross sections that are perpendicular to the x-axis. So here we have in terms of x, so it means that the slices are being cut straight down, so they're being perpendicular to the x-axis. In that case, we're going from A to B, which is farthest left x to the farthest right x, and the variable we're using is x. We could also have cross sections that are perpendicular to the y-axis. So in this case, the cuts are being made perpendicular to the y-axis. So we're going to use an integral that's going from C to D, meaning your lowest y value to your highest y value. And then we're doing everything in terms of y. Okay, so same type of idea. So before we get into an actual problem involving this stuff, I just want to kind of illustrate what we're doing. So when you see my bad drawings, they make a little bit more sense. Okay, so we're going to look at this really quickly. So here we have two functions. We have the red function and we have the blue function. So this is my 2D image. So if I were to make cross sections that are perpendicular to the x-axis, let's say I pick squares. Right? If I increase the number of squares, this is all I see in 2D. Doesn't really make much sense. I can pick equilateral triangles, and I'm going to pretty much see the same thing in 2D. So what I'm trying to do here is show you in three-dimensional form here what they kind of look like. So if I move this, bear with me while I get, the right orientation, not that way, we'll do it like this. So the red is the x-axis, the blue is the y-axis. No, the green is the blue. The green is the y-axis. The blue is like your z third dimension. Okay. So if you look at it from a different way here, let's say I want to use squares. Okay, so here's my three-dimensional square. The more squares that I have, let's increase the n, which is the number of squares. The more squares I have, I start to get a three-dimensional shape. So the more squares I have, it makes this 3D shape. And it's very hard to visualize it because you can't really draw it unless you're fantastic at art. And if you are, please show me your drawings. But this is pretty much what we're doing. We're trying to find the volume of the solid that's created when we put an infinite amount of whatever shape they're asking for that are perpendicular to whatever axis. So these are all squares. So let's get rid of the squares for a second. So let's look at equilateral triangles. Okay, so here's triangles. The more triangles I have, okay, I'm going to get a shape. So the shapes are very similar, but they're different depending on the actual shape that we're using. Okay, and let's look at the semicircles. Okay, so here's some semicircles. Again, if we increase it, we're going to get a different shape, but same type of idea. There's some three-dimensional image that we're going to get when we increase the number of whatever shape we're using. All right, so now we're going to look at an actual example here. So I apologize for my drawings. So we're going to find the volume of the solid bounded by the graph y equals the square root of x equals 4, and the x-axis using cross sections of squares with a base that is perpendicular to the x-axis. Okay, so the first thing that, whenever we're doing these problems, the first thing we want to think about is what shape are we using, and are we doing it perpendicular to the x or to the y? So if we're doing it perpendicular to the x, we'll use dx, and you're going to use x as your variable. If you're doing it in terms of y, you're going to use dy and y as your variable. So here we're using, I'm going to underline here, squares and x-axis. So here's my two-dimensional drawing. Y equals the square root of x is this function up here, and then x equals 4 is this line here. And I'm making my cross sections perpendicular to the x-axis, so I'm going from top to bottom here. If I were to make this into a three-dimensional drawing, and again, I apologize for my terrible drawing skills, but you can see that the blue y equals square root of x is this top thing. Right here is the x equals 4. And then I tried to draw these squares and then create the 3D image by drawing this. But it's not super important that you can draw them or like even visualize what it's really doing as long as you understand the concepts. So if it's helpful to draw them out, great. If not, I would at least try to just draw this green graph up here so you at least know what direction you're going in terms of perpendicular to which axis. All right, so we know that we're using squares, so I'm just going to draw a little square here. So each one's going to be a square. We know that the area of a square is going to be base times base, which is going to be base squared. So area is base squared. So our base, when we're figuring out what our base is, the base is always going to be the top function minus the bottom function. All right, so the top function is going to be the square root of x, and the bottom function is just the x-axis. So that's just y equals 0. So top function is square root of x, bottom function is 0. So my b is square root of x. So my area, since it's b squared, is going to be the square root of x squared, which is just x. So when I go to write my volume here, volume is going to be equal to the integral. I'm just going to write it out this way first so we can see. From a to b of the area, a of x, times the width, which is d of x. So we can see that from left to right, our x's are going to go from 0 to 4. The area we figured out was x because it was the base squared. And then the width is going to be dx. So now I'm just taking the antiderivative of x, which is going to give me 1/2 x squared. And then I'm just going to evaluate it at 0 and 4. And then if I do that, plug in 4 and then minus 0. So that's just going to give me 8. Okay, since I don't have any units or anything, I don't need to label anything. It's just going to be the volume is equal to 8. Okay, so let's look at another one. So write but do not solve an equation for the volume of a solid bounded by the graph of y equals 6, y equals 4 ln of 3 minus x, the y-axis, and x equals 2. Using cross-sections that are squares with a base that is perpendicular to the x-axis. So similar to the last problem. So I'm going to draw this one out real quick. So here's our, and I'm only going to draw the 2D version, don't worry. So we have the line y equals 6, which is up here. We have y equals 4 ln of 3 minus x. So that's going to be something like that. We have 0 and we have x equals 2. So this is going to be 2. Here is 0. So we're doing cross-sections that are squares and perpendicular to the x-axis. So we're going to have our bases look like this. So just pretend that these are the little bases of the squares. So we know that each square is base times base. So our area, again, is going to be base squared. So here, our base is going to be the top function. So the top function is 6 minus the bottom function. The bottom function is 4 ln of 3 minus x. So my area is going to equal the base, which is 6 minus 4 ln of 3 minus x squared. So we figure out the base based off of the functions that we have. The area is going to be that base squared. And for this one, we don't actually have to solve it. All they want us to do is write the integral. So volume is going to equal the integral from 0 to 2 of the area, which is 6 minus 4 ln of 3 minus x squared, times the width, which is going to be dx. Okay, so there's a lot of problems that are on the AP exam, that the ones that feature the perpendicular cross sections, a lot of them are just to write it and not solve it. So the main idea here is that you can write it. Once it's written, it's just what we've done before with solving definite integrals. Okay, so let's look at this example. Find the volume of the solid bounded by the graphs of y equals the square root of x equals 9, and the x-axis using cross-sections that are isosceles right triangles with a base that is perpendicular to the x-axis. So I'm going to sketch this graph. So y equals the square root of x, that's going to be that graph. X equals 9 is going to be like here. Okay, and now I'm using isosceles right triangles. So the base is perpendicular to the x-axis. So here are like my bases of my different right triangles. All right, so I'm looking here. So here's B and here's B. So the area I'm using is going to be half B squared. So my B is going to be the square root of x because it's my top function, which is square root of x, minus the bottom function, which is the x-axis. So that's just 0. And then my area is going to be 1/2 the base, which is square root of x squared. So that's just 1/2 x. So when I go to find the volume, I'm going to have the integral from 0 to 9 of the area, which is 1/2 x, times the width, which is dx. So I'm actually going to pull out the 1/2 because that's my constant. So I can pull out the 1/2 integral from 0 to 9 of x dx. So now when I take the antiderivative of x, that's going to give me 1/2 x squared. And then I'm evaluating it from 0 to 9. So I plug in 9, I'm going to get 81 over 2 times 1/2, so 81 fourths, minus 0. So I end up with 81 fourths. Okay, if you are going to use decimals, just make sure that you use at least 3 decimal places. Okay, so here, another example. The base of a solid, S, is the area beneath the line y equals 1 minus x, enclosed in the first quadrant, bounded by x equals 0 and x equals 1, has perpendicular cross sections to the x-axis that are semicircles. Find the volume of S. Okay, so let's do a quick little sketch. So 1 minus x is going to be this line here. And it's in the first quadrant, bounded by x equals 0 and x equals 1. So I'm just going to, right here, call that 1. So we're really looking at this shape here. It's perpendicular to the x-axis. So again, we're drawing our base straight down. We're using a semicircle. So remember that the area of a semicircle is pi over 8 base squared. So the base of each of my semicircles is going to be the top function minus the bottom function. So the top function is 1 minus x. The bottom function is 0. So my base will be 1 minus x. My area is going to be pi over 8 times my base, which is 1 minus x squared. So I'm just going to write this as pi over 8. And if I square 1 minus x, that's going to give me x squared minus 2x plus 1. So for my volume, I'm going to have the integral from 0 to 1 of the area. And since I have this pi over 8, that's a constant, I'm actually just going to pull that outside to begin with. So the volume is equal to pi over 8 times the integral from 0 to 1 of the area, which is x squared minus 2x plus 1, times the width, which is dx. So I have pi over 8 on the outside, and then what I'm going to do here is just take the antiderivative of x squared minus 2x plus 1. So I get 1/3 x cubed minus x squared plus x. And then I'm evaluating that from 0 to 1. So I end up getting pi over 8. If I plug in 1, I'm going to end up with 1/3. If I plug in 0, I get minus 0. So I end up with pi over 24. Oops. So let's look at this last example here. So now we're going to look at it going the other way. So here we have R is the region enclosed by y equals 4 square root of 9 minus x and the x-axis in the first quadrant. Region R is the base of a solid. For each y value, the cross-section of the solid taken perpendicular to the y-axis is a rectangle whose base lies in R and whose height is y. So usually when you're dealing with a rectangle shape, they will tell you either what the height is or something about the height so you can figure it out. So since we know the base always has to do with the functions, the height itself, they have to give you some further information. So here we don't have to solve it, it just says express the volume of the solid with a definite integral. So we know since we're doing it perpendicular to the y-axis that we're going to be using dy for the width. So our entire volume has to be in terms of y, it can't be in terms of x. So the first thing that we're going to have to do is change the function. So we have y equals 4 square root of 9 minus x, but we need to change it and solve it for x because we need it to be in terms of y. So the first thing I'm going to do is divide by 4. So y over 4 is equal to the square root of 9 minus x. I'm going to square both sides. So I'm going to get y squared over 16 equals 9 minus x. And then to get x by itself, I'm going to move the 9 over and then divide by a negative. So I'm going to get 9 minus y squared over 16. So this is the function I'm going to be using because now it's in terms of y. Okay, so since I'm going perpendicular to the y-axis, my base is going to look like that. It's going from like right to left or left to right, whatever. So when we're finding the base, first of all, we know area is going to be base times height. To figure out the base in this case, since we're doing it perpendicular to the y-axis, will be the right function minus the left function. So the right function is going to be what we solved for, which is 9 minus y squared over 16 minus the left function, which is just x equals 0, so just minus 0. So that's our base. Our height, they told us, is y. So when I go to find the area, it's going to be 9 minus y squared over 16, put that in parentheses, times y. So for the volume equals, we're going to have the integral, and because we're doing this in terms of y, our bounds are going to be from our lowest y to our highest y. So we're going from 0 to 12. So that's the lowest y and the highest y. And then we have, I'm just going to put the y in front so it doesn't look as silly. So we're going to have the area, which is y times 9 minus y squared over 16, times the width, which is going to be dy in this case because we're doing it perpendicular to the y-axis.